Okay, welcome to this presentation. I'm Vincent Werner and I'm a PhD student from the CEREC Grenoble and Verimag. And today I will talk about fault injection and how to optimize the fault injection equipment with optimization techniques. So let's start. So first, how do we inject fault? Well, we can use any technique that will alter the microcontroller environment locally or globally. The most popular techniques are laser fault injection, electromagnetic fault injection, and power glitch. And once we have chosen one technique, we have two things to do. So first, we need to know when to inject faults. So for that, we must find vulnerabilities on the target application. And to do that, we can use binary analysis, for example, or symbolic execution. Some of these techniques are in this paper, but this is not in the scope of this presentation. And the other thing we have to do is to calibrate the equipment. That is, find the best settings to inject fault. And each fault injection techniques has a specific parameter space, and depending on the complexity of the parameter space, difficulty to find the best settings is not the same. So for example, with the power glitch technique, we must find the amplitude of the glitch and the duration of the glitch. So usually the parameter space is small and we can identify easily the best parameters even with a brute force approach. But with electromagnetic fault injection, we have 5 or 6 parameters to adjust, and as a result, the parameter space will be much bigger, and we cannot use brute force approach to identify the best combinations of settings. So for this situation, we need techniques to identify the best settings. And to do that, we can either reduce the parameter space or we can explore the parameter space more efficiently. So to reduce the parameter space, we can use techniques to identify hotspots on the target. For example, we can use the optical beam induced current to find the most active regions of the chip during execution. And then with laser fault injection, for example, we only focus this region of the chip. So usually these techniques are effective, but often they are not generalizable to other fault injection techniques. For example, if we want to do power glitches, we cannot use optical beam induced current. So we must use optimization techniques to explore the parameter space more efficiently. And the first technique we can use is the grid search. So the grid search is an semi-exhaustive search on a predetermined range of values, and it's very popular, but it's only effective with a small parameter space. We can use random search, which is in theory better than grid search, and to understand why, we can take this example on the right. So here we have parameter space with 2 parameters. So the red parameter is not important, and the blue parameter is important, and there is an optimum right here. With grid search, we only sample 3 different values of the blue parameter, and we miss the optimum. And with random search, we sample 9 different values, and we identify the optimum. But both techniques have the same limitation, which is that the next configurations to be tested are chosen independently of the previous results, and consequently many evaluations are wasted on poorly performing configurations. Another way to optimize the equipment is to use genetic algorithms. These algorithms are based on the evolutionary theory and have been applied to electromagnetic fault injection and power glitch technique. So how does it work? So well, we start by initializing a population with random settings. Then we evaluate experimentally these settings to see if we can get a faulty result with them. And next, once we have tested all the population, we want to evolve this population. To do that, first we select based on a strategy two different settings. With these settings, we mix them using a crossover operator to generate a child. And then we apply a mutation on the child to generate a new setting that will be part of the new generation. And we repeat the selection, the crossover on the mutation steps until all the population has been renewed to form the new generation. And we repeat the whole process until we reach the last generation, and usually the best settings should be in the last generation. So this algorithm is simple to implement and it is better than grid search and random search, but there are two main limitations. First, we have to adjust many hyperparameters, for example, the number of generations and the selection strategy. These hyperparameters strongly influence the final result. The other limitation is that genetic algorithm can suffer premature convergence. That means that we can be stuck into a local optimum, which is not good. But hopefully, new optimization techniques have been proposed over the last decade, such as the BANDIT algorithm and Bayesian optimization. These techniques are already used in machine learning to optimize machine learning models, but they are not applied to fault injection to optimize parameters of the fault injection equipment. During this presentation, we will present you these techniques, and later we will evaluate them with a new approach that will be also presented. And finally, at the end of this presentation, we will do a quick demonstration on a real-world example. So first, I want to talk about the successive halving algorithm, which has been proposed by CARDIS in 2013 to solve the BANDIT problem. The name of this problem comes from this machine, which is also known as a one-armed bandit. We can imagine a gambler in Las Vegas who has to decide which machine he has to play in order to maximize the sum of rewards within a limited budget. So he can either keep playing with the best machine he knows, so in that case it's called exploitation, or he can try different machines to find a better one, and in that case it's called exploration. And the bandit problem is all about this trade-off between exploration and exploitation in order to maximize the sum of rewards within a limited budget. So let's back to the successive halving algorithm and our problem, which is to find the best setting. So first, we have to define the maximum number of fault injections we can do, and then we choose randomly n initial configurations. We allocate the total number of fault injection evenly across log n eliminations rounds, and at the end of each round, we divide by 2 the number of configurations, and we keep only the best ones. And we multiply by 2 the number of evaluations for each remaining configuration. And finally, we repeat this process until one configuration remains, and it should be the best one. So this algorithm is simple, but there is one question: how to choose a number of initial configurations. We can either take a small number of configurations, and we test them a lot, or we can do the opposite. In the first case, we can do more exploitation, and in the second case, we will do more exploration. One solution proposed by Aziz in 2019 is to take the largest number of configurations possible for the budget. So in that case, we have a budget equal to n log n, and as a result, during the first round of this algorithm, we will select aggressively configurations after just a single test. For example, if we have a budget of 24 fault injection, we must take 8 configurations randomly, and we test them only once during the first round. And in the next round, we divide by 2 the number of configurations, keeping only the best ones, and we increase the number of tests. And finally, we repeat this process until one configuration remains. So this algorithm is simple to implement, but yet we will see that it can be better than genetic algorithm in some situations. SMAC is another interesting algorithm I want to talk about. It is based on Bayesian optimization and it has been applied to optimize hard combinatorial problem solvers. Also, SMAC can handle non-deterministic processes, and this is useful because with fault injection, the same settings don't lead to the same result. Sometimes you have a fault, sometimes you don't. Also, SMAC can support all types of parameters, including continuous, discrete, and categorical. But the main difference of SMAC in comparison with previous optimization techniques is that SMAC tracks of the past result to fit iteratively a probabilistic model. And to do that, SMAC is based on 3 main steps. First, we fit the model based on previous results. Then we select configurations based on the model. Next, we test the selected configurations to generate results, and we repeat the process. We fit the model, we select the configuration, and so on. And also, because SMAC is based on Bayesian optimization, it has 3 main elements. The probabilistic model, also called surrogate model, the selection function, which is also called acquisition function, and the intensify mechanisms, which does not exist in the classic Bayesian optimization approach. So first, the probabilistic model. It is based on random forest, which is an ensemble of multiple decision trees. Because we want to use continuous values as the leaves of the trees, the decision trees are called regression trees. So how does it work? Well, first we have to take the previous result, in that case the 4 parameters and the fault probability. To generate a tree, we start by randomly sampling n results with replacement, and after that we choose randomly again m parameters to split the root node. We keep the ones that minimize the sum of the squares of the residual, and we continue until we reach the maximum depth of the tree, and we'll repeat this process for each tree of the forest. Then, to estimate the fault probability of a new configuration, we simply take the average estimation of each tree. Next part is the selection function. In SMAC, this function is based on expected improvements, and it is used to quantify how much a new configuration is better than the current best configuration known. To compute this function, we need the prior distribution of fault probability. So that's why we need the random forest model. And this function will try to keep the balance between exploitation by sampling where the model predicts the highest fault probability, and exploration by sampling where the model has no prior knowledge. And finally, the last element of SMAC is the intensify mechanisms, and this mechanism contributes also to maintain balance between exploration and exploitation. To do that, these mechanisms adjust automatically the number of tests for each configuration, and also it updates the best configuration known so far. I won't go into details, and more information can be found in this article. So SMAC seems very good and very powerful, but it suffers from one main limitation, which is that initial conditions can greatly affect the convergence speed. And we need that at least one configuration generates faulty results. Otherwise, SMAC will struggle to identify the best settings because it doesn't know what a good configuration is for our problem. So to solve this issue, we add an additional 2 steps procedure. First, we do a pure exploration, that is a random search until we find at least one working configuration. and then we apply mutation on this working configuration in order to generate an initial population of settings for SMAC. And by doing so, we are sure that we have at least one working solution, and SMAC will have a reference to work with. Of course, depending on the target microcontroller, we can adjust the pure exploration step and find more working configurations, for example with secure microcontrollers. So far, we talk about optimization techniques such as SMAC and successive halving algorithms, but we didn't talk about methodologies yet. One interesting approach has been proposed by CARPI in 2013 to split the optimization problem into two stages. First, they identify the best settings independently of the injection delay, and then they determine the injection delay. So basically, first they found how to inject faults and then when to inject faults. By doing so, they reduce the parameter space by removing the injection delay in the first step, which speeds up the optimization process. One important detail is that they use a target application to identify the best settings and to determine the injection delay. In the following slides, we will combine SMAC and successive halving optimization technique with this two steps methodology. But there is a main difference with the previous approach, because we will use test programs to identify the best settings instead of using the target application. Why? Because test programs are designed to maximize fault propagation in order to identify faster the best settings. With the target application, the injection delay is important and it can be difficult to ignore it completely. But with test programs, the delay is not important because the same instructions are repeated and we can control the program state of the microcontroller. Also, the synchronization with the microcontroller is easier. So our approach is based on two different steps. First, we have the calibration stage to identify the best settings using SMAC, for example, on the test program. Then, once we have identified the best equipment settings, we find the injection delay on the target application with random search or grid search until we manage to get a successful attack. We can use random search or grid search for the exploitation stage because there is no need for optimization. So now we will evaluate the optimization technique on the calibration stage of our approach. We will evaluate SMAC, successive halving algorithm, random search, and genetic algorithm. To evaluate these techniques, we will compare the fault probability evolution over 50,000 fault injections. However, it can be difficult to compare the results because SMAC and successive halving algorithm only return a single configuration, whereas random search and genetic algorithm return multiple configurations at the end. So to solve this problem, we need a post-processing that depends on the technique. For SMAC, the best configuration is automatically updated, so we don't need post-processing. For random search, every 5,000 fault injection, we inject 1,000 more faults to estimate the fault probability of the best configuration known so far. For genetic algorithm, we do the same as random search. And finally, for successive halving algorithm, at each halving, we evaluate the average probability of the remaining configurations. To evaluate the optimization techniques, we will use three different microcontrollers, one Cortex M0, one M3, and one M4. We will use this test program to maximize the fault propagation, in particular the corruption of instructions, which is very common with power glitches. So why I say power glitches? Well, because we will use this setup, which is a low-cost glitcher based on a simple system to convert an 8-bit digital signal to analog glitch. With this setup, we can adjust 8 different voltage levels to adjust precisely the glitch waveform. Because we have 9 free parameters, the parameter space is big, really big, so we have to use optimization techniques to identify the best settings. So after 50,000 fault injections, we get these results. For each microcontroller, we have the fault probability evolution over 50,000 fault injections according to SMAC in orange, genetic algorithm in red, random search in green, and successive halving algorithm in blue. For example, 0.8 fault probability means that we can inject successfully 8 faults out of 10 injections. So if we look closely at the results, we can see that SMAC is significantly faster than other techniques and that SMAC finds better configurations than genetic algorithm. On the other hand, successive halving algorithm is slower by design, but it can identify better configurations than genetic algorithm or SMAC. But there is one issue with successive halving algorithm, which is the fact that it spends too much time on poorly performing configurations during the first halvings. So to sum up, based on this result, SMAC seems the most interesting optimization technique for our problem because it is fast and efficient. In the following, we will compare SMAC and GA using our two-step optimization approach. We will show that SMAC can be used to exploit vulnerabilities faster than with genetic algorithm on the real example. More precisely, we'll try to reproduce a known attack presented in this paper. Using fault injection, they can extract the user application from the flash memory of a STM32F1 even if the readout protection mechanism is activated. This mechanism prevents any read operation on the user flash memory using a JTAG probe or the embedded bootloader. We will reproduce this attack, but we will use during the calibration stage only 6,000 fault injections in order to show that SMAC is much faster than genetic algorithm. The attack is simple. We send a read memory command using the embedded bootloader. Then, when the device is checking if the readout protection is on or not, we inject a fault using our setup. And finally, we check if we receive an acknowledgement or not. If we don't, we repeat the process until we get one successful attack. So during the calibration stage of our approach, we only inject 6,000 faults during 15 minutes. And we can see that SMAC is much faster and we can find a better glitch waveform than genetic algorithm. Also, we can see that the best glitch waveform found with SMAC is very different with the one found with genetic algorithm. And finally, using the best configuration found, we try to reproduce the attack during the exploitation step of our approach. With SMAC, the attack is easily achieved within 5 minutes. With genetic algorithm, after more than 12 hours, there is no result, so we decide to stop the experiment. Then we reproduce the experimentation, this time with 12,000 fault injections during the calibration step of our approach. But still, SMAC finds better glitch waveform than genetic algorithm. So now I will show a quick demonstration of SMAC on the STM32F1 using our setup. So here we have the script to do the attack. First we configure our equipment and SMAC, and then we launch the first step of our additional procedure, which is pure exploration. So as you can see, we test a lot of different configurations with a random search. Finally, once we have found some working configurations, we apply mutations to generate the initial population for SMAC, and then of course we run the SMAC optimization. So at the beginning we get only 3 faults out of 10 injections, but quickly after that, after some iterations, we managed to get 9 faults out of 10 injections, which is really good. So then, with the best glitch waveform, we try to bypass the readout protection mechanisms. So first we try to run readout fault to show that we cannot read the flash, and then we inject the fault during the readout protection check, and we can read the flash memory. To sum up this presentation, we have presented recent optimization techniques, and especially SMAC, which is significantly faster to identify the best equipment settings. We also presented an approach to identify faster the best settings using a test program instead of the target application to quickly determine the best parameters. For the future, we plan to test SMAC with electromagnetic fault injection and laser fault injection. We want to see if the motors can handle fast movement on the X and Y axis without moving the microcontroller under test. Also, we want to see if we can bypass hardware countermeasures such as glitch detector with SMAC. Finally, we plan to test other recent optimization techniques, for example, Hyperparam. So thank you for watching my presentation, and bye-bye.